Welcome back, AP Stat students. We are entering the last throes of Unit 2, which is Chapter 10. And I hope we are now able to put everything together for a least square regression line or model. And this idea of throw me to the wolves and I will return leading the pack is, I know this is going to be slightly difficult, handling these curvilinear functions. But if we take this piece by piece, we can apply everything that we saw and be able to linearize it. So the idea is we're going to be re-expressing the data and manipulating data values to find the line of best fit. And the focus really is finding lines of best fit, because all of our regression analysis up to this point is all about lines. So with the homework, and do note, solutions are at the end of the notes. If you need help, and many of you will, you can check back for solutions to each and every problem that's listed here. Now, our objective is re-express data to find lines of best fit. Well, what does that mean? When we talked about correlation and regression, the assumptions that we've made is that one, quantitative variables. We are dealing with two quantitative variables. Our scatter plots are sufficiently linear. So a linear model assumes the relationship between the variables is linear, and then we check the linearity of the regression analysis by looking at the scatter plot of the residuals. Remember, we don't want to see nothing in the residuals. That's the good thing. We don't want to see a pattern in the residuals. The last couple things that I know they're forgotten about because we haven't made a whole big issue, but we want consistent variance. So check for changing spread in the residual scatter plot. And last bit, outliers. Check for leverage and influence in individual data points. So all the things that we focused on in Chapter 9, come back here. Consistent variance we've kind of seen before, as if the residual starts scattering or gets more concentrated the further you go along in the X, that's something to note and worry about. Now, additionally, the fundamental assumption for working with a linear model is that the relationship you are modeling is, in fact, linear. That is our basic assumption. And it may be difficult to determine the scatter plot of the data you're looking at, that the model is not truly linear. Sometimes it looks linear, but we're not sure. It is possible we miss a curve in a scatter that you plot the residuals. We cannot use a linear model unless the relationship between the two variables is indeed linear. If we can mathematically manipulate the values to straighten a curvilinear relationship, we can then fit and use a simple linear model. So the most common ways to re-express data are with exponents, roots, logarithms, and reciprocal functions. Now you might be thinking to yourself, we haven't really done these complex mathematical operations in this class so far, and I agree with you. So we're going to walk you through a little slowly, and it's more about the understanding. I will say the AP loves logs. And in fact, most of the time that you are presented with this, they're going to give you the re-expression to linearize the equation. So don't worry that you have to really do this type of analysis, but I want you to be prepared to do it. So re-expressions are done every day in the real world, and re-expressions is not cheating, but we must report re-expression in our model. What do we mean? So given the relationship between miles per gallon, looking at weight of a car, and then the fuel efficiency in miles per gallon. We're looking at late car models to earlier car models. And we look at the scatter plot, and it may be reasonable to say that our data fits a line of best fit. But if we run our linear regression analysis, obviously heavier cars tend to take more fuel to move. The scatter plot shows a strong negative linear association between weight of a car and its fuel efficiency. If we ran the model of this scatter plot, we get an R of negative 0.911. The linear regression equation is miles per gallon hat is equal to 49.4 minus 8.79 times the weight of the car. So what does this mean in context? We need to define the elements of the regression equation. So we're looking at the weight of a car and then its fuel efficiency. What does the slope mean? Well, for every additional 1,000 pounds, of vehicle weight, miles per gallon, will decrease by 8.79. What else should we be able to identify? Our y-intercept. So we always interpret both of those values. A vehicle weighing 0 pounds will get a predicted fuel mileage of 49.4 miles per gallon. Now note, these are our squishy words. We are not using, at 0 miles, you will get a fuel efficiency of 49.4 miles per gallon, because statistics is squishy. We always want to leave ourselves some wiggle room when we're reporting these out. Now look, if we look at the residual plot, we see something not kosher. And just to highlight this for you, the residual plot goes down and then comes back up. Remember, ideally, the scatter plot of the residual show no pattern. There is definitely a pattern going on here. So another look at the initial scatter plot of weight and fuel efficiency does show a slight curve. Now, for some of you, you might not recognize that curve. Like maybe that looks like exponential decay. Let's say e to the negative x. For others of you, you go, oh, that looks like a 1 over x function. Either of those cases might be more linear if we want. And so the idea is taking that curve, a linear function, and being able to re-express it. So what might we do to improve this model? Because we can see that it's curved, not a line. The data is perhaps sufficiently linear to use a linear model. After all, r squared is 0.8299. I mean, 82.99% or 83% of the variability in miles per gallon or fuel efficiency is due to the variability in the weight. But it is possible to improve this model. So instead of looking at miles per gallon, like we normally do in the US, we could do like what most of the rest of the world and consider number of gallons per mile, or more usefully, the number of gallons per 100 miles. And instead of looking at miles per gallon, and we look at gallon per 100 miles, doesn't that look like a 1 over x function, or the reciprocal function? If we flip those, so notice, what gets changed is the y-axis. We can re-express fuel efficiency as gallons per 100 miles, which is a reciprocal, and eliminate the bend in the original scatter plot. So does gallons per mile make sense? In this case, we see that we now, instead of having that negative bend, as weight increases, the more fuel it takes to drive 100 miles. That's how we interpret the slope. Again, we should look at the residual plot to confirm if we see a pattern. And we look at the residual plot for the new model, seems more reasonable. I mean, there are some outliers really far away, but in general, we don't see that distinct pattern that we saw before. So the idea of straightening out these are to improve our model to make better predictions and analysis of the data. So our goals for re-expression, we'll go through the goals, and then second part will be a couple example problems. Goal number 1. We cannot use the regression concepts on skewed distributions. From everything that we've done, we can't say linear least square regression lines for skewed data. But re-expressing the data may make the distribution of a variable more symmetric. For example, if you're looking at assets for companies versus the number of companies, we can see that this is skewed to the right. But what we can do is, if we see that this is skewed to the right, we might maybe take the log of assets and look at the exponents. And by taking just the log of the assets, we get a much more symmetric distribution of data. So at this stage, we should be comfortable investigating symmetric relationships. We've done it a handful of times. And so by making things more symmetric, they're easier to analyze. Goal number 2, we can make comparisons of multiple distributions if we make the variability more alike, even when the medians are very different. So take a look. Our medians could be drastically different from stage to stage. But again, by taking the log of assets, then it concentrates things because logs are only looking at exponents. And so we're comparing exponents that shrinks the number so they're easier to compare. Goal number 3, our primary purpose in re-expressing data is to find a linear relationship by making the form of a scatter plot more nearly linear. The goal in this basic statistics class is to linearize. Because all of the techniques that I've taught you so far focus on lines. Are there ways of analyzing things that are exponential, or quadratic, or root functions? Absolutely. And further statistics classes provide those for you, but they are beyond the scope of this class. Goal number 4, re-expressing data can make the scatter in a scatter plot spread out evenly rather than being compressed in one area. So everything's down here below, and then it jumps up, looks like a exponential growth. Well, what we can do then is take the logs of both variables to linearize. This can be seen in the 2 scatter plots we just saw. So log of 1 versus the assets, log of both, now we are looking at the linear version. And this gets to this idea of the ladder of powers. Now, I'm going to put up an image shortly that goes through each of the steps on the ladder. But I don't want you to focus too much on that, but I want you to think it comes from this curve. So there is a family of simple re-expressions that move data toward our goals in a consistent and systematic way. And this collection of re-expressions is called the ladder of powers. The ladder of powers orders the effects or the transformations that re-expression have on data. The further the transformation from one, the greater the effect on the data. Changing the sign of data or opposite values simply keeps the original direction, not necessary, and I do not approve. So you could change the sign, but then it throws a monkey wrench and everything. So I don't think you have to actually change signs of data at all. What we are going to do is apply operations to rescale. That's the idea. So here are our powers. Normally, we start at 1, and this is just your original data. But we could move up and we can square, or we can go down and square root. So square, linear, square, root. We have O to go drop down. If anyone's taking calculus, you think the derivative of 1 would be 0, but this is our log function. And then negative 1/2 would be the reciprocal square root function, and negative 1 would be our reciprocal function. So the image that you see in front of you has the ladder of powers. So I want you to think, if we're staying at 1, that's our raw data. That's where we want to be. That's most of our linear stuff. If you want to move up the ladder to 2, try with unimodal distributions that are skewed to the left. If I want to drop down on the ladder and say square roots of the data values, counts often benefit from a square root re-expression. For counted data, we're going to start here. We'll use logarithms here if we have to drop down further. So measurements that cannot be negative often benefit from a log re-expression. If we have the negative 1/2 or reciprocal square root, it's an uncommon re-expression, but sometimes useful. And then the reciprocal function that we saw is the ratio of 2 quantities, think miles per hour, often benefit from a reciprocal. When trying to re-express data, try the smaller transformations first and work your way up. If the initial transformation seems to help, but not enough, go the next step or stronger on the ladder. So either keep going, or if the initial transformation makes things worse, you went too far or the wrong way. So go the other direction on the ladder. Just like Goldilocks, you are trying to find the re-expression that is just right. And I will say this one more time, and then we will end the video here. AP loves the logarithm. When no data values are 0 or negative, logarithms might be just right. Logs are not as extreme as taking a root. So try taking the logs of the predictor variable, the response variable, or both variables. Then re-express the data using some combination of log of x versus y, or x versus log y, or log x versus log y. Or, if you also like the natural log, which of course I do, ln of x, ln of y, or ln of x and ln of y. So this next video is just going to walk you through some basic properties of logs. We'll do a couple examples and go over the mathematician's idea of where this ladder of power comes from. So I will see you all in the next video, Falcons.